Thanks for joining me again. Today in this tutorial we will be looking at the internal forces of a distributed load, namely a triangular distributed load. We'll start off by discussing the load, then we'll figure out the reactions before we go on to solve the internal forces. And at the end we'll have a little summary of what we've discussed so far. Let's get to it. Now before we move on to discuss the free body diagram and the reaction forces, I just want to have a look at this distributed load. Now, as we've discussed before, whenever I have any distributed load, it doesn't matter what shape, the equivalent force of that distributed load is the area. Okay, so in this case, it'll be the area of a triangle. We have here 6 meters in length and 9 kilonewtons over meter for the height. So the force, the equivalent force, is always going to be the area, and in this case it's 9 times 6 over 2, which gives me 27 kilonewtons. And I can see that the units are correct, right, because I've got kilonewton over meters times meters, and that gives me kilonewtons. So that is the equivalent load that this distributed load applies on the beam. Now the question is, where does that sit? Where do I put it? For every distributed load, you apply that resultant force or that equivalent force at the centroid of the shape. So for a rectangle, that is in the mid of the cross section, and for a triangle, it's a third from each of these right angled sides. So it'd be a third L from here and 2/3 L's from here. So in our case, that would be 2 meters and 4 meters, and here is where my equivalent load would sit. Okay, so that distance is important. I mean, if I was doing moments around here, then this would be the distance I would need to take, 2 meters. If I was doing moments around A, for example, I would need the 4 meters. So now that we understand how the distributed load works, we're ready to create our free body diagram and to find the reactions. So I can see that at point A, I've got a pin support, which means that I've got 2 reactions here. Let's draw them in, AY and AX. And at B, I've got a roller support, so just one reaction of BY. And I'm just going to do this in a very systematic approach, summing all the forces in each direction. I'm going to start off with the forces in X, with this being my positive X direction, and in X I've got AX, but no other reactions or forces, so AX equals 0. Then if I do the sum of forces in the Y direction, with this being my positive Y, I've got AY plus BY, and then minus this distributed load, which we already found is 27, but just to clarify, it is the shape, so it's going to be 9 times 6 divided by 2 equals 0, and as we already found, that means that AY plus BY equals 27. And the last thing I'm going to do is sum of moments around A, with this being my positive direction, and for this I've got a positive moment from BY, so plus BY times 6, and then minus that distributed load, first the area, so that is the force, which equals the area, and then times the distance, which in this case is 4 meters. Okay, so that is the distance from the centroid to the point that I'm looking at. Okay, so essentially what it is this distance here. And there is nothing else to contribute to moment, so that equals 0, and I can see from this that 6 BY equals 108, and therefore BY equals 18 kilonewtons. And now that I know that, I can come into this equation here, and I can write out that AY equals 27 minus by, so that is 27 minus 18, and therefore ay equals 9 kilonewtons. And that makes sense because there is much less of the distributed load next to point A than there is next to B, so it does make sense that at B the reaction force will be higher. And now my last thing to do really is to put the values of the reaction forces where they belong. So AX we already agreed was 0, AY we just worked out as 9, and BY we just worked out as 18. So let's put them in here, all ready to solve the internal forces. Now, one very important thing to clarify, I need to solve the internal forces for this thing with a distributed load. It is not the same as solving the internal forces for this thing, okay? First of all, this just gives me a point load, and the bending moment would look very different. It would look something like this. Whereas we can already see it would not be the same case for the distributed load. So I'd get very different bending moments. And the reason would be if I cut this beam here, I only have, as you can see, those are my internal forces, I only have this point load. There's nothing else happening here, which is not the truth for the distributed load case. And therefore, even though this equivalent load helped me find the reactions, I cannot continue using it to find the internal forces. Now that we've figured out the reactions and we understand how this force works, it's time to look at the internal forces. We'll take a bit more time discussing shear and moment because it is quite critical to understand how the force works in this case in order to get the correct diagrams. Let's get started. Let's start looking at the internal forces. The first thing that I want to do is I actually want to draw that segment of beam that I'm looking at. And I can see that this triangular load is across the whole beam. There's no change apart from the change in the load itself. So I'm going to cut somewhere between A and B and figure out what is happening. So if I look from A towards B, I'm going to have my 9 kilonewtons reaction force. I'm going to have some part of this triangular distributed load, and I'm also going to have, to balance this all out, my internal forces. So the axial force, the shear force, and my bending moment, all drawn in what we agreed on as the positive sign convention. X will start from here, and X will go between 0 and 6 meters, right? Because this load, although it varies, it is still the same load across the whole beam. I'm going to start off with my axial force because that is going to be the easiest, and I find this by doing the sum of forces in X, and I can see here that I only have nx in the x direction and nothing else, so that is 0. A quick and easy win here, and I can just draw that straight onto my diagram here. So just a line, and I'm just saying it's 0 in case anybody doesn't see that that's a straight line. The next thing that I want to find is my shear force. Now, this is something that is quite important to understand. As we mentioned before, the force at any given point is that area, the triangle. So if I'm at 1 meter, it's going to be a triangle of 1 meter. If I'm at 2 meters, it's going to be the area of the triangle for 2 meters, and so forth. But at each of these distances, I will have a different height. So what I want to do is I actually want to find the function for this triangular load first. And how are we going to do that? We're going to use knowledge that we have from before. So we know that, let's just call this function Wx. Wx is a linear line. And we know from before, for a linear line, we can write that as ax plus b. And all we need are 2 known points to find out what a and b are, and then we'll have the whole function. Now, I do know 2 points because I know that at point A, here, right, I know that at point A, I have 0, 0. So when x equals 0, there's also 0 load. So that's point A. And I also know what's happening at point B. So I know when I get to 6 meters, I know that my load is 9. And just doing this very slowly, I'll remind you that I just need to substitute these in. So A, using the first point, times x equals 0, plus B equals W, which is 0, I find out that B equals 0. And if I substitute the next point, 6 and 9, it means that A times 6, B is 0, so I can ignore the B, and that equals 9, and therefore A equals 9 divided by 6, which is, of course, 1.5. So I can find out that the load function is 1.5 x. And that means that if I know x, for example, 1 meter, I know that the height of that triangle, which is the force, is 1.5. If x equals 2, then I have 1.5 times 2, which is 3. When x equals 6, I have 1.5 times 6, which is 9. So now I know that function, it makes it much easier for me to find the area of the triangle for any given x. So now that I know that, let's do the sum of forces in the y direction. So I've got 9 going up minus sx going down, and also minus the area, which gives me the force. And the area is going to be wx times x over 2. Okay, so wx gives me the height of the triangle, x gives me the length of the triangle, and divided by 2, because it is a triangle, equals 0. So s equals 9 minus wx is 1.5 times x, and then times another x, and then divided by 2. And so sx equals 9 minus 3/4 x squared. And that is my equation for shear. Now it's interesting to note here that this equation has x squared, so it is a parabola, which is interesting because if you remember from the UDL, in the previous tutorial, with the UDL, my shear was linear, it was a function of x. Now with this DL, distributed load, I have a function of x squared. I know obviously it's going to be interesting to see what happens at some different locations, so let's check what happens when x equals 0 and what happens when x equals 6, so when I reach point B. So when x equals 0, I can see that the x part falls off and I just have 9 kilonewton, which matches the reaction that I have, so that's great. When x equals 6, I've got 9 minus 3/4 of 6 squared, and that works out as minus 18 kilonewton, which is also good because it matches my reaction force. So here I've got 9, here I've got 18, and I know that this is a parabola between them, so it's going to look like this. And the question that we need to ask is, where is this 0 point? Because this 0 point is important for me being able to know where my min or max moment is. So let's start off with that and then figure out a bit more on how this looks. So in order to find out where that 0 point is, the easiest thing for me to do is say s needs to equal 0. So at what x does 9 minus 3/4 of x squared equals 0? So 3/4 of x squared needs to equal 9. X squared therefore equals 9 times 4 divided by 3, which is 12, and therefore x is plus minus 3.46. That's mathematically. Now in terms of our exercise, x can only be a positive number, right? So it has to be 3.46 meters. And that means that this distance here to 0 is 3.46 meters. So that's the first thing. The second thing is, how do we know that this is the shape? And probably the easiest thing to do in order to determine that is just to add a few more points. So what happens, for example, at half that distance from A to 0? So when x equals 3.46 divided by 2. So that means what happens when x equals 1.73. Let's see. So I've got 9 minus 3/4 of 1.73 squared. And if I quickly calculate that, that works out as roughly 6.75 kilonewtons. Now, if this was linear and this was a straight line here, we know that at the middle it would be 4.5, right? At the middle. But actually it's 6.75, which means it is higher than that half mark. And so you can see why it's drawn like that. And we can do the same exercise on this side and find out that actually if we're drawn a straight line, if it was linear, then this point here would be higher than what we get. And that is how we can figure out the shape of this parabola. Obviously, you can use other methods like looking at this mathematically and figuring out the shape. That's all valid. These are just some of the ways that you can do that. And the last thing we want to do is we want to find the internal moment. So we're going to do sum of moment at the cut, with this being my positive moment direction. And if I'm doing moments around the cut, I've got the moment itself, which works out as positive, so mx, and then I've got minus 9 times x. And then I've got a positive moment from this distributed load, so plus, and then as before, I need the area, which is 1.5x times x over 2. Okay, that is the area, which equals the force. And then I have to multiply that by the distance from the centroid. So let's just remember that wherever my x stops, the centroid is always going to be 1/3 of the length from the opposite side, from this side here. So it will always be times 1/3 of x, and that equals 0. So mx equals 9x minus this thing here, which is going to be 1.5 divided by 6, and that gives me 1/4. So it'll be x cubed divided by 4. And this is the equation for my moment. Now, once again, I want to check a few critical points, and they will be what happens when x equals 0 at point A, what happens when x equals 6, point B, and what happens at that point where the shear crosses 0. So what happens when x equals 3.46 meters? So at 0 I can see that I get 0 immediately. When x equals 6, I've got 9 times 6 minus 6 cubed divided by 4, and that gives me 0, these two things that I'm expecting. And now let's put in that point of max or minimum. So 9 times 3.46 minus 3.46 cubed divided by 4, and I get 20.78 kilonewton times meter. And now I want to draw that on. I also want to note that this is also a parabola, but cubed, right? It's a function of x to the power of 3. And the last thing I need to check actually is, do I draw it on the top, so on this side, or do I draw it on the bottom, on this side? So if that was my beam, I assume that my moment was like this. That means that moment is pulling at the bottom and pushing at the top. Since I got a positive answer here, that means that my assumption was correct and it's pulling at the bottom, which means that tension is at the bottom, which means that this is the side that I'm going to draw my moment. So 20.78, and it's parabolic, so something like that. So just a few important things before we finish. When we have a distributed load which is not uniform, we can see that our shear is a parabola, and it's a function of x squared, and our moment is also a parabola, but it's a function of x cubed. As we saw before, when the shear is at 0, we get our maximum or minimum moment, and our shear starts from our reaction force and ends in the reaction force, and our moment starts at 0 and ends in 0. And that's us. Today we had a look at a simply supported beam with a distributed load of a triangular shape. We looked at the free body diagram, developed the reactions, and also the internal forces. We also had a look at the internal forces and discussed some of the differences that we found comparing to different loading types that we had. And the next step is to put them all together, to introduce some distributed loads with some UDLs and some point loads and see how we get on. Join me next time to do this. Bye for now.